Right, good morning, everybody. Looks like things are kind of working, so that's good. Um, we're going to start chapter 6 today, which is about electronic structure of atoms. And what that kind of means, by the way, this is not on your second exam, so if you want to focus your energy on thermochemistry and come watch these next week, you are just welcome to do that. So just keep that in mind. So your exam on Monday is just chapters 4 and 5, so not this one. So we're going to deal with how electrons are distributed throughout atoms, and kind of a little bit, and just a little bit about how they behave. And when we're talking about behavior here, it's really their interactions with light. So it's not really about chemical reactions per se. It's more kind of physical interactions. You could call it chemical interactions, but kind of just looking at one atom and one set of electrons by itself. So we're kind of just focused on one thing at a time here. So in order to do that, though, in order to see how electrons interact with light, we have to talk about light first. So, although this chapter is on electrons, we're going to see that by talking about light first, that's going to help set us up in the correct way for talking about electrons. So let's talk about light. Couple things. We'll see that light is an electromagnetic wave. It's got an electric field and a magnetic field component. We typically, though, don't draw both. We just draw one, typically the electric field component. So it just looks like a regular wave. There's a couple of bits on this wave that we're going to want to talk about so that we have names for these when we look at energies and all that sort of thing. We're going to see that this distance here is called the wavelength. And that is given the Greek letter lambda. And that's because it's a length, it's going to be in some units of meters because it's a length. We're going to see that we have also something that we don't talk about much. Is this difference here that's called the amplitude. And that relates to how intense the light is. So we're going to see that the color of the light and the type of light will be dependent on the wavelength, but the intensity of the light is the amplitude. So it doesn't matter how big your wave is in terms of determining how much energy it might have. That's all about the wavelength. So we're going to see that in just a little bit. Another component we have is called the frequency, and that's basically traveling at light speed, just how often um, we traverse a wavelength. Bit wordy, but the frequency is just how many wavelengths you're able to get through in a second. So you're traveling at light speed, that's 3 times 10 to the 8th meters per second. Your wavelength is some sort of meters. The frequency is just telling us how many of those wavelengths we're able to go through in a given amount of time. Typically, that's 1 second. So the units that we use for frequency are hertz, which is 1 over seconds, inverse seconds. So how many per seconds? Like RPM rotations per minute that your engine in your car goes through is also a frequency. But that's in minutes per minute, right? Frequency for light is per second. So how many wavelengths per second that we're going to go through. And so that's what the frequency is. One more bit for us to know is that electrons do travel roughly at the speed of light, although we're talking about light, so of course it is traveling at light speed. This is the speed of light here. And we're going to be able to interchange three of these things. The amplitude we're not really going to talk about, so amplitude goes out the window. But wavelength and frequency we're going to talk about a lot. And so we're going to see that the speed of light is going to be what is going to help us interconvert between them. Right? It turns out that the frequency will be equal to the speed of light over the wavelength. Or you can rearrange this equation however you like. By the way, that's the Greek letter nu. It's not a V. That is nu, a fancy V. So I try to draw it a little bit fancy, so it's not velocity, but it's frequency. So that's the Greek letter nu, a little bit of a squiggly. It's like a cursive V, kind of, but hard to do just writing. So, anyways, so the frequency is equal to the speed of light over the wavelength, and we can tell if we ever forget this because we have meters per second over meters, which gives us 1 over second. So the units do check out. So remember, if you ever forget formulas, which you don't really need, just look at the units. If you know what quantities you're relating together, just look at their units. And you'll see that the units here will tell you the same story that your formula will. But I understand there is comfort in formulas, so you're welcome to use that. So this means that frequency and wavelength are inversely proportional. And maybe that makes sense. If frequency is how many wavelengths we could do, and we're traveling at the same speed all the time, if we have a very long wavelength, we're going to get through fewer of those going at the same speed. But if our wavelength is very short, we're going to go through a lot of them. So we're going to see that frequency and wavelength inversely proportional. That means when one goes up, the other goes down. So frequency goes up, wavelength goes down, and vice versa. All right, because everything's traveling at the speed of light, so that's a constant. We don't have to worry about it. And so we're good there. While it is important to talk about kind of the wavelength and frequency of light, they're very important properties. What's probably more interesting to us or more useful to us is the energy. Energy of a photon. A photon is a unit of light, kind of like one wave, one unit of light. It's simply a constant times the frequency. And this constant, I'm going to have all these different colors today. This is Planck's constant. Used all the time in talking about light. So physics, chemistry, we use this constant a lot. 6.626 times 10 to the negative 34 joules times seconds. So notice H is joules times seconds. Frequency is 1 over seconds. So that means our unit of our energy of a photon is in joules, which makes sense because we just spent an entire chapter talking about all sorts of thermal energy in joules, right? We use joules as our predominant unit there. So we'll see that the units again work out here. We could also say, if we wanted, I'm going to just copy that equation. Since we know the frequency is c over lambda, we could also say that the energy is hc over lambda. And so we can relate the energy of a photon with its wavelength or its frequency. And we see here that the energy of the light, aka the light, the photon is the unit of light, just one unit. Like we use atoms for matter, we talk about photons for light. So we're going to see that it is directly proportional to frequency and inversely proportional to wavelength. So as your frequency goes up, your energy goes up. As your wavelength goes up, your energy goes down. So we'll write those out. So as frequency goes up, energy goes up. As wavelength goes up, energy goes down. So they are inversely proportional. So we'll see that because the wavelength and frequency are also inversely proportional, this all works out. So we're going to see that we can talk about light. Very commonly, we talk about light using wavelength. That's our kind of most common way of talking about it. And so understanding that a longer wavelength means lower energy is an important part for us. So a lot of the, do I want to talk about 5G and the hilarity of that? We could, but we'll do that later. First, I want to talk about kind of different flavors of light, and then we'll do some calculations. So, something you've probably seen before, the electromagnetic spectrum. Generally, we kind of start this with high energy and low wavelength on one side. So remember, those are opposites. And then we have low energy and long wavelength at the other end. Kind of right here. Oh my gosh, go away. Okay. Right here in the middle, I don't want to say the middle, this little blob here is the part that we can actually see with our eyes. And we're going to see that this will be I'm going to have to put all my colors here. We're going to have a rainbow here because we'll see about those colors and how they relate to this. Hey, that's pretty good. I did a good job. Okay. We see that this is visible light, thusly named because we can see it. This is what our eyes can interpret as light. So we see colors. That's all a construct made by our brains. So colors don't really exist. It's our brain's way of identifying, hey, this light is lower energy than this light. So we're going to see that this is about 700 nanometers. This is about 400 nanometers down here. And so that's the range of wavelengths that we can see is between that. And we see also that the red side is the lower energy, longer wavelength, The purple side, or the violet side, is the higher energy side of visible light, and therefore has the lowest wavelengths. If we go a little bit higher energy or longer wavelength, we have the ultraviolet region. So past violet, right? Violet purple is our highest energy visible light. As we go higher energy, we have UV light, ultraviolet. And it's this light that has enough energy to um, cause double bonds to start doing weird things. We'll see what double bonds are later on. This is what causes sunburns. Um, we don't typically like UV light, right? Because it can cause damage by messing with chemical bonds. So that's the region that kind of damage can occur. And in fact, anything higher energy, including UV, can cause damage. We see if we go past UV, we're getting into the X-ray region. So UV goes to about 100 nanometers or so, so between 100 and 400 thereabouts. And the X-rays go to about 0.1 nanometers. So X-rays, much shorter wavelengths, much higher energies. And of course, we know X-rays, we don't want to be blasted by them all the time because we're going to have all sorts of bad things happen. So, you know, we are already kind of aware that the X-rays are higher energy. And then higher than that, we have gamma, which I'm going to just rewrite. So we have gamma rays that are even higher energy than X-rays. Those are things seen more in space or by very radioactive nuclei. So we don't typically deal with those. But those are even higher energy. Those are to be avoided at all costs. So if one of you ends up going into space, which may or may not become a thing soon, who knows? That's why if you like leave your spacecraft, you have all to have all this super protective gear. It's not really. I mean, yes, the thermal part is a problem. Space is incredibly cold, but it's also the fact that you have complete exposure to all these very high energy light rays, and so you'll like immediately get just zapped with radiation if you don't have your spacesuit on. Anyways, on the other side of things, we have the infrared here that goes up past this, and this goes to kind of maybe about 1,000 micrometers or so, thereabouts. And so infrared light we kind of interpret as heat. You might have like infrared lamps or something like that. We typically can feel those, but we can't see the light rays. Uh, Various other animals, by the way, can see certain UV or IR wavelengths. IR cameras you also use as kind of thermal cameras if any of you are in the military or play Call of Duty or whatever, like your night vision goggles. Those are infrared detectors. So they transform infrared light signals into something your brain can process, because our brains cannot process UV or IR light or any others besides visible light. So um, there we have that. So typically it's heat that we sense. That amount of energy is enough to make bonds vibrate. So in UV and X-ray, we can actually break bonds apart. We can zap electrons out of atoms, do all sorts of crazy stuff that's ionizing. Infrared light is pretty weak. It can make things vibrate. That's all. And as we start increasing, we go to microwaves, which go into the kind of maybe 100 centimeters or so. Microwaves can only make things rotate. So that's how they heat up your food, by the way, is you completely zap your food with a ton of microwave light, and that rotates water molecules. And by doing so, it causes friction with other water molecules or other things, and that's where the heat comes from. So interestingly, if you take a cup of like sugar or something or salt, throw it in the microwave, zap it for 5 minutes, you can immediately put your finger in that salt or sugar and no problem, because the microwaves are specifically tuned to use a wavelength that is specific for water's vibration and rotation. So fun fact. So of course, don't stick your finger in water that you've just microwaved for 5 minutes. It'll be boiling or very hot, and so not a good idea. The last one, the lowest energy we have, are radio waves, and those can go to kilometers long. So portions of miles or miles long if you think about the wavelengths. So by the time that one wave goes all the way up and all the way down, it's taken kilometers. Those are our lowest energy um, waves of light, and those are radio waves. So this is Wi-Fi, cellular phones. Um, what else? Radio, of course. Radio waves, TV waves, all that sort of thing is radio energy. Very low energy. So all these things about the 5G causing cancer and all that, it's kind of bogus. Sorry to say. uh, because in order to have enough energy to mess with chemicals, you've got to be at least in the UV range. So radio waves, microwaves, they can't really do much. They can heat things up maybe through friction, but that's it. So they directly cannot cause harm for us. So that be that. So visible light far worse for you energy wise than radio light is. So looking at something purple is technically more damaging. Actually, no. Looking at something, I guess, orange is more damaging to you than no, purple because it's absorbing orange. It's reflecting purple. Never mind. We'll talk about that next semester. If you continue on, we talk about transition metal chemistry. That aside, that's our spectrum. So we have ways of classifying light. And we can now talk about some of these things. Let's see, for example, what is the energy in joules of a photon with a wavelength 400 nanometers? Let's do some math. So, energy we're looking for, we're given wavelength. So, we're going to probably want to use the formula that has those two things. H and C are both constants. So, if we want to do this, we'll write everything out. Planck's constant, I'm just going to write for us. You'll get very familiar with it as you do the homework for this. Speed of light. And then we have 400 times 10 to the negative ninth meters. Remember, nanometers is 10 to the negative ninth. So I'm going to put some sig figs on this too, by the way. Don't forget your metric stuff, right? We can't use nanometers directly because we want it to cancel out with meters, right? We want our seconds will cancel out. We want our meters to cancel out too, so we have to use meters. We can't use kilometers, we can't use nanometers, micrometers, whatever. It has to be meters. So just don't forget that. All right, and after this, it's just a matter of doing the math. And I do not have a calculator, so to the Google we go. So let's see, 6.626 times 10 to the negative 34 times 3 times 10 to the 8th divided by 4 times 10 to the negative 9th. We do this. and we get 4.97 times 10 to the negative 17 joules. And indeed, this does not seem like a lot of energy. So, what's the point? Well, this is one particular photon. Very often, we don't deal with just one. Just like we don't deal with one atom at a time, we deal with many, right? Moles of atoms. So sometimes it's important for us to say, okay, well, what's the energy of a mole of these? Because that would be something that might be a little bit more relevant to us. So that's one photon. What is the energy of a mole of photons 400 nanometers is their wavelength. So we know that this is technically joules per photon, and we have a number that can cancel out to give us joules per mole, right? How do we go from joules per photon to joules per mole? Well, just like anything else, we can say there's a certain number of photons that will be a mole, and indeed, here is a conversion factor, not negative. Remember that one mole is Avogadro's number of anything. Doesn't matter what that is. So photons, we'll say. So if we have joules per photon and we want joules per mole, how many joules in one mole? And we can just use this. We can say, aha, we have our 4.97, which we probably shouldn't have rounded because we're now doing other things with it, but whatever. Joules per photon times, we're going to put photons on the top, and if we do this, I'll take my answer here, divided by 6.022 times 10, I'm sorry, multiply it by, not divide by. Apparently I can't, so this is what I'll do. I'll make this, yeah, that probably would work. No, it won't. All right, I gotta delete it all. Okay, times 6.022 times 10 to the 23rd. There we go. All right, and so we get, why couldn't have given this to me in a better way? 29926.329 joules. So now we're seeing this is indeed a lot of energy. Let's see, 1, 2, 3, 4, 5, 6. So we'll say maybe this is 29.9 megajoules of energy. So, or we could say 2.99 times 10 to the 7th joules. Either way. So both of these, we have quite a bit of energy here. This is a lot of energy. And this is just a mole of photons of that. So if you have a mole of photons of purple light coming at you, that's a lot of energy that you have to deal with. So, we're going to see that this is consequential. So there are consequences for these. If you have a much smaller wavelength, except in UV wise, we're going to see it just gets higher and higher and higher. These energies get higher and higher. So that would be technically megajoules per mole. So there we have it. Alrighty. Any questions so far? Is this stream like working today, by the way? It looks good on my end, but I just want to be sure. It looks okay. So I'm thinking we're in good shape, but we'll go on from there. All right, any questions on that one? So you can do all sorts of fun things. We can do, here's one, the Wi-Fi band is 5 gigahertz. What is the energy? In joules per mole. What's 1 mole of Wi-Fi waves coming at us? So there are two main Wi-Fi bands, right? You have 2.4 gigahertz and 5 gigahertz. So we'll go with the higher frequency one. So giga, remember, is 10 to the ninth power, right? So 5.0 times 10 to the ninth, 1 over seconds. Don't forget the unit hertz is 1 over seconds. So that's what we're looking at here. If we're looking at energy, it's simply h nu. We have nu here is 5 times 10 to the ninth. That's our giga. So 6.626 times 10 to the negative 34 joules times seconds. Multiply that by 5.0 times 10 to the ninth per second. Or the seconds will cancel out. We're left with joules. This will be joules for 1 photon, but let's go ahead and do it. And we'll adjust it later. 6.626 times 10 to the negative 34 times 5 times 10 to the ninth. 3.313 times 10 to the negative 24 joules. And if we want to do it for a mole, if we multiply it by Avogadro's number, 6.022 times 10 to the 23rd, we get 1.995, which runs to 2.0 joules per mole. Wow, what a difference. So 30 million joules for visible light we can see, that is coming into our eyes all the time, versus the Wi-Fi 2 joules. 2 joules versus 30 million joules for 1 mole. So 2 joules is not a lot of energy. That's not even enough to raise 1 gram of water by 1 degree Celsius, right? So 1 gram of water is 1 ml, which is 1/5 of a teaspoon. So it's a tiny amount of energy. Tiny, tiny, tiny for an entire mole of these photons. So keep that in mind. If we want to, no, we'll leave it there. So that's the idea here. Like Wi-Fi and stuff, not gonna kill you. You're fine to use your Wi-Fi all you like. So don't go looking at purple things though. That'll kill you. But you'll be just fine with Wi-Fi. Oh no, and I'm using purple as one of my colors here. Uh-oh, I'm killing you slowly. So that's the idea. So we can take a frequency, convert it into an energy. We can take a wavelength, convert it into energy, and we can go from there. All right. What's this got to do with electrons, though? We're going to see that there's a couple of things that can happen when light and electrons interact. Let's see. When light and electrons interact. And really, it's kind of the same thing, but to the second one's to a higher degree. So the electron absorbs the light and becomes excited. And we'll see what that means. Option two is the electron absorbs the light and gets ejected from the atom, meaning it gets so much energy that it just goes away. It's gone. It's out of there. And the third one, which is very most often, is that the electron does not absorb the light. This is the most likely scenario. Um, and we're going to see why. But the other two options are possible. We're going to talk about number two first. So, light causing electrons to get ejected. We're going to see that this is something called the photoelectric effect. And this is how your solar panels work. Is you've got your solar panel here. Here comes your lovely light beam. Woo! Goes in, and what happens is an electron gets blasted out of that material. So this is a light beam, this purple thing. Light we usually just abbreviate h nu to indicate a photon. So we have light coming in, electron gets zapped out. And so this is how solar panels work. Those electrons then are carried down, they cause current and all sorts of, I don't know the electrical terms, but that's how it works. So the light comes in, it has sufficient energy, the electrons absorb it, they get very, very excited, so much so that they are actually ejected from the atom. And then they go off and do electron things and power your cell phones to do whatever you're doing, looking at memes instead of paying attention in class or TikToking. So, whatever it may be. So that's how this works. This is, it works for a lot of applications. So not only is solar panel is probably the most industrially important, but there are a lot of kind of analytical techniques that also rely on this as well. So like kind of working with um, old artwork or whatever, if you want to discover things about your surface of something, there is photoelectron spectroscopy, which is pretty interesting, but that's advanced analytical stuff, so that's beyond this course. And so that's just something that could happen. So it's something that solar panels happen to undergo. Typically, this is the case with metals, by the way, that tend to do that. So, but that's all right. Let's look at scenarios 1 and 3. Electron does or doesn't absorb the light. Either it does or it doesn't. It's an absolute. There's no partial absorption. We're going to see that electrons can only absorb very specific photon energies. And so if you're shining, say, a white light on something, I mean, we know that, this, I don't really have a good example. I do. this OChem book has certain areas where certain light is going to be absorbed by the material. So this particular thing is absorbing this kind of reddish light, um, so it depends on the atoms that are a part of that pigment or paint or whatever or ink on that book. They're absorbing specific ones, and it all depends on the atoms that are involved here. Certain elements absorb very specific, or no, all elements absorb very specific energies. However, those vary from element to element as to what those energies are. And we're going to see that. I'm going to hop over to Wikipedia for a second, actually, so we can take a look at some of these. They kind of first discovered this idea. Oops. Which shall we look at? Let's look at hydrogen first. And let me switch the screen over so we can see. New window. Go. So hydrogen. What we're going to look here is this little bit here. If you see, there are a few of these lines that are very distinct, right? We have this kind of dark blue one, this light blue one, this red one. These are specific to hydrogen. And we'll see a couple more. How about we look at lithium? Notice lithium has green, orange, different red than the hydrogen had. Lithium's a pretty simple element, only 3 electrons. Let's look at bismuth, 83 electrons. Let's see what we've got here. Very, very many now. We're going to see that because we have so many electrons, we have all sorts of different energies that are absorbable by our bismuth atom. So each element has its own kind of spectral lines, as they're called, and these lines correspond with the energy that is being absorbed by the electrons. Let's do a couple more. Let's look at thallium. Thallium's interesting. It's got that really good green one. Yeah. Thallium actually, very interesting, only has this one green one. We're going to see that sometimes um, some of these energies are in the visible region, which is what we can see here. That's what these spectral lines correspond to. And sometimes they're not. So in the case of thallium, we just have that one super vibrant green one, and that's the only energy we have for thallium. Despite it having 81 electrons, only one of them is able to absorb energy in the visible range. And let's look at just one more. How about neon? That's one you're familiar with. Super red, right? When you look at it. Look at neons. Even though there's only 10 electrons, got lots of stuff, lots in the red, right? So we see that all of these, they're unique for every single element. All right, so that's the idea here. And let's go back here. Oops. So, no, I don't want new tags. Important part is each element has specific sets of these. And that all of the elements have different ones. So what may be absorbed by a hydrogen atom may not be absorbed by the bismuth atom or the thallium or whatever. So those kind of, it's all about which thing we're looking at. And we're going to see that these correspond with energy levels within the atom. These photon energies these correspond with energy levels within an atom. And we call these, by the way, these very specific sets, these very specific energies, we call these quantized absorption. we can only absorb certain ones. We can't exist with a whole set of different energies, only specific ones. And the word for that we use is quantized. They're very specific, discrete, exact levels that we can have. And all of these, every atom will have its own set of quanta, its own quantized energy levels. So, one way I think the book does a nice job of it is it compares, by the way, something like a ramp versus a staircase. If you are a person going up this ramp, here we are, we're going up this ramp, up we go. I can exist, or you, whoever's on this ramp, can exist anywhere you want on this ramp, any energy level you want. You could exist here, 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 or even here. Whatever, anywhere you want to exist. However, if you're on the staircase, you can only exist at specific levels. You can't exist halfway up a step, right? So this is a continuous spectrum of energy. This is a quantized spectrum. So you can't exist halfway up a stair, but you can exist half a step up this ramp. You can exist anywhere on that because it's continuous. However, with the stairs, you cannot exist halfway up a stair or even just a portion up a stair. It's either you're on one stair or you're on the next stair. That's it. Quantized. Very specific levels. All right. Continuous, on the other hand, you can do wherever you want. So our atoms and all that are going to behave much more like this. So we're going to see what those levels kind of correspond with. And so this takes us kind of into one of the older models of the atom, the Bohr model. Where we had different energy levels. And those energy levels were what corresponded with the differences in energy that could be absorbed by the electrons. We're going to see that if we take our hydrogen atom and we give it some, we give it some energy, we end up exciting it if it's absorbed. And let's take a look at what that looks like. For us in the Bohr model, I'm going to, instead of doing it circularly, I'm going to do it just kind of linearly. This could correspond to an electron getting excited and going up to the next energy level. This axis here is energy. So if we want to draw it as like a graph or whatever, we don't really have an x-axis, but I'm going to get rid of that actually. We're going to see that these energy levels have a distinct amount of energy between them. N equals 1 is not zero energy. There's some energy there. So if we do draw the axis, we see that zero energy is not there. We don't exist at the zero energy level, right? Because we're not at absolute zero. So things are still having some amount of energy regardless. And so, again, we can't really describe exact energy levels, but we can talk about the difference of energy between two levels. And that difference of energy is going to be equal to the energy of the photon that is absorbed by the atom. So the difference in energy is equal to the energy of the photon. Your photon's energy, which will be its frequency times Planck's constant, must equal the difference in energy between these two energy levels. And the reason that the energy levels are different is because electrons, negatively charged, like to be close to the nucleus. The farther you go, the more they want to go back, right? They want to be as close to the nucleus as possible. So by pushing it farther away, you're giving it extra energy. So you're moving it to a higher energy level. Same with gravitation, right? The farther you go from Earth's surface, the more the Earth wants to bring you back towards it. And so you see that you have a greater energy difference the farther you are from the surface of the Earth than if you're just standing on it. So if you're skydiving, you are obviously being pulled close to the Earth. You have a lot of potential energy there. It's the same thing for electrons. The farther you go from the nucleus, the more energy you have because you want to be pulled back towards it. So that's what can happen with electrons. You give them extra energy, they end up jumping up to a new level. We call this the ground state, by the way, and this is an excited state. It's got more energy. That's the excited state. Pause this somewhere down there. So we're going to see that the energy that is absorbed is exactly equal to the energy level difference. And so it's going to be very useful for us to say, aha, well, this particular atom has absorbed this photon. We can see what the energy difference is. And we're going to see for all atoms that the difference of energy from 1 to 2 is always bigger than 2 to 3. Is always bigger than the difference between 3 and 4, and so on. So that kind of first gap is always the biggest one. And so if you want to look at them on like a graph again, n equals 1, 2, 3, 4, 5, 6. I don't know why I'm making these narrower, but the point is they get closer and closer together. So the energy gap is always biggest from the first one to the second one. And so we see here that the energy E1, I'm calling it, is bigger than E2, which is bigger than E3, which is bigger than E4. So uh, the differences farther and farther out make less and less importance. So now, interestingly, after it absorbs it, what can happen is it just spits that photon back out again. And again, this has exactly equal energy to one of these delta E's, whichever one it happened to be. If this was an electron moving from n equals 2 to n equals 3, it would have a specific energy. If it was n equals 1 to n equals 2, that's a specific energy. N equals 1 to n equals 3, that's another one. So we have all sorts of different options here. All right, so let's see what we can actually do with this. So we can actually calculate these energy states for hydrogen. I have a formula for us here. We can calculate these energies for hydrogen. The minute you go to helium and you add more than one electron to the system, oh my gosh, it gets crazy. The amount of math required to work with a helium atom instead is astoundingly high, because then you have to factor in electron-electron repulsion. You You have to figure out what's going on with this electron and then what's going on with that electron. It's a lot more work. So we typically only calculate these for hydrogen. But the point is that while we can get the numbers for hydrogen, the same patterns will apply for every other atom. So we're going to see that. We're going to just do this for hydrogen. So the energy of the photon is going to be three constants, which I don't remember one of them. This is the Rydberg constant. Rydberg. It might be a U. It's going to be that value times 1 over n squared, whatever n happens to be. Remember that n can be anywhere from 1 to infinity. We don't really talk about infinity. We usually are limited to 7. We're going to see that these n's correspond with the period on the periodic table. So since we only have 7 rows on the periodic table, that's typically where we end this. But in theory, it can go up to infinity. And nobody likes dealing with all these constants. So we just kind of combine them. And we'll give it the numerical value for this. So it's negative 2.18 times 10 to the negative 18th joules. So we don't ever have to worry about HC and RH. Just use this number to represent all of those. And so if we want to calculate the energy of the n equals 3 level, you can figure it out. Oz is having some trouble. 1 second, we gotta get him out. He's under the covers trying to get his way out of there. All right. There you go. Okay. So if we do this, it's quite a simple calculation. N is 3, so we'll just put 1 over 3 squared. It's kind of, it's an interesting calculation. It's not going to be very useful for us, but let's do it anyway. Negative 2.18 times 10 to the negative, 2.18 times 10 to the negative 18. Yeah, there we go. Times 1 over 9. We get negative 2.42 times 10 to the negative 19. So totally, this is normal to have a negative number. The reason for this is because we assign 0 to the maximum amount of energy. So that's why this is negative. And we also do it because when we talk about energy levels, we're going to we frame it so that we'll get a positive answer when we emit a photon. So that aside, this corresponds, this is negative because 0 is defined when n is infinity. So when the electron has left the atom, that's when we say it's 0 is the energy level. So, by the way, that's joules. So if we try to do this for n equals infinity, that's 0, right? So we set our 0 to be the infinity. So once we're out of the atom, once we're no longer even part of that atom anymore, that's our 0 point. And so that's why we're going to get negative numbers for these. All right. So let's take a look at some things. Let's see, what about determining, how do we use this? Well, more often, what we're actually doing instead is we're looking at delta E. Because E itself for hydrogen, yeah, it can be calculated, but who cares? Not very important to us. What's more important is delta E, because we know that photons can be absorbed corresponding to the energy difference between two levels. And so this is going to be a little bit more useful for us. And so we're going to see that delta E will be our kind of, just like any other thing, our final state minus our initial state. And that's going to be equal to the same constants. And using both of the energy levels here. And we'll see how to use this equation. So let's say, what about, let's go from n equals 2 to n equals 4. This is absorption. And let's see what this is going to be. So we're going to have we're going to start at n equals 2, that's our initial one. And we're going to be going to n equals 4, so we're absorbing a photon. Let's see what the difference of energy is going to be. So the difference of energy for 2 to 4 be 1 over so 1 over 16 minus 1 over 4. I don't want to do that. This is what calculators are for. If we do this, swap over to our calculator, aka Google, negative 2.18 times 10 to the negative 18 times parentheses 1 over 16 minus 1 over 4. And we get positive value 4.0875 times 10 to the negative 19 joules. Where are we here? OBS, there we go. No sig figs for this really because we don't really have any measurements. This is all theoretical stuff. So no sig figs here. But let's see what wavelength this corresponds with. What wavelength is this? Let's see if we can see this light that would be absorbed. If we do that, we have energy equals hc over lambda. So if we want to solve for lambda, lambda is hc over E, which will be all of our lovely constants, speed of light, and then our energy here, 4.0875 times 10 to the negative 19 joules. Lots of fun with exponents on our calculators today, isn't it? It's a pain when you have to type it into Google, so that's my reminder to not forget my calculator next time. Times 10 to the negative 34 times 3.0, why am I writing that? Times 10 to the 8th divided by 4.0875 times 10 to the negative 19. Alright, we get this. This happens to be 4.86 times 10 to the negative 7 meters, which is equal to 486 nanometers, which is light we can see. So this particular one is probably going to be kind of like a blue-green light. This happens to be an energy that falls in the visible range. And so if we go to hydrogen, let's see if I'm totally just making this up right now. Let's see if hydrogen has a blue-green light. Oh, you've seen me use my calculator, en.wikipedia.org. Whoops. Let's see if hydrogen has got one of these for us. Do we have something blue-greeny? Aha, there it is. So this middle line here, the light bluish one, that's the one that's corresponding with this 486 nanometers. So we see that for hydrogen, we do see three lines that we can see. So three of these energy levels are visible light. And so we do see that this energy difference between 2 and 4 is something visible to us. So, ta-da, we're able to calculate that just by using this information for hydrogen. Again, we can only calculate this for hydrogen, but let's leave that where it is. So that's what we can do with all this stuff. If we were emitting the light, by the way, the process would be the same thing. If we were emitting, if we're going 4 to 2, it would be the opposite, right? It would be the opposite because it's just a sign change. When this happens, we always kind of use the absolute value. Because again, it's a change in energy, so there is some directionality to this. Which way is it starting? Which way is it ending? If we're going to use this number, use the positive one. So we usually say negative delta E for emission. Or we can say more practically, just use the absolute value. Just use the absolute value in your calculations. Because obviously you can't end up with a negative wavelength, right? There's no such thing as a negative distance. There is for displacement. You can go backwards, but not for distance. So can't have a negative there. So as a result, just use your absolute value. So because if you were to calculate this from 2 to 4, you get positive 4 point whatever. If you calculate it for 4 to 2, the opposite one, where 4 is your initial, 2 is your final, you'll end up with a negative number. So you always want to use the absolute value. So just keep that in mind for some of your homeworks. Right? How is that? Plenty of problems for you to practice with this. So have fun. All right, let's talk about a few last things here. And so we're going to kind of transition into electrons a little bit, although not quite. We're going to fully transition to electrons on Thursday. So it turns out that all matter can have a wavelength. And this is called the de Broglie wavelength. So, and this is going to be, interestingly, it's a way of talking about electrons specifically, but we can see it technically could apply to regular things like me. I would have a wavelength too, but it's going to be Planck's constant and the momentum of your object. Generally, this is done for electrons. This is the fundamental part of electron microscopy. So if you know anything about light microscopy, there are limits to how big of things we can see just using light. But we can actually get much smaller wavelengths of electrons than we have available to us light waves. And so just because of the physics of how microscopes work, there's just only so much certain wavelengths of light that you can use in a microscope. So, but electrons have no such limits. And so we actually use very high energy, very short wavelength electrons to do microscopy. And so that's how we get electron microscopes. So if we want to think about doing this, I have the numbers here for like actual electrons because I have no idea what electrons weigh. Okay, here we go. Let's say an electron is it's got a mass of 9.11 times 10 to the negative 31 kilograms. Tiny number, right? And we're gonna say it's not going the speed of light. It's going a little bit less. Let's say this one happens to be going at here. Let's say we're going at 7 times 10 to the 7th meter per second. So not quite the speed of light. So with these two, we can figure out its wavelength. So let's do it. Planck's constant. Feel like you've probably already memorized it just by writing it 15 times now. Mass and velocity are our momentum, so we'll put that there. 9.11 times 10 to the negative 31 kilograms. And then the velocity, 7 times 10 to the 7th meter per second. One thing to note, a joule, by the way, I'm going to get rid of that. A joule is a kilogram meter squared per second squared. So joule times second is kilogram meters squared per second. So I'm going to just put that there. Kilogram meters squared per second. So notice, unit-wise, we ain't going crazy here. Kilograms cancel. Meters per second cancels the second and one of these meters out. So we're left with meters as our answer. And let's see what this electron happens to have as its wavelength. So 6.626 times 10 to the negative 34 divided by 9.11 times 10 to the negative 31 divided by 7 times 10 to the 7th. And this one happens to be an X-ray electron, apparently. So we're looking at 1.0, let's say 1.04 times 10 to the negative 11 meters, or you could say 10.4 picometers. I'm sorry, 104 picometers. So smaller, this one is a pretty fast moving electron, pretty high energy. So very low wavelength here, picometers level. So don't forget your metric prefixes. I have another one for you, by the way. 1 angstrom is 10 to the negative 10 meters. So this would be 0.104 angstroms. So that would be the case as well. So you may see angstroms a lot here. The angstrom is the unit that's 10 to the negative 10 meters, typically used for talking about atomic size or X-ray wavelengths. So this particular one happens to have energies in the X-ray level of light. So fun stuff. Alrighty, one more bit before we do this, and this is the Heisenberg uncertainty principle. And altogether, instead of teaching us how to make methamphetamines, this principle actually tells us that we cannot know the exact position and momentum of a small object at the same time. And so this principle tells us we can't know exactly where an electron is if we know how fast it is. And so it's a way of just kind of understanding physics a little bit. It's how we can't know both of these things at the same time. So we can know how fast it's going, but we don't know where it is exactly. There's some uncertainty in its position. Or if we know exactly where it is, we have very little idea of how fast it's moving. And the smaller your object is, the greater this uncertainty is. And so we have a way of talking about this. So this tells us it's formally written that your change in position times your change in momentum is always going to be greater than h over 4 pi. Don't worry about that. We're not going to use this one. We'll say, for example, if we're to try and calculate the position of an electron, well, we can say it's going to be greater than h over 4 pi mv, we can say. And so we'll just go ahead and use this, and we can just go ahead and make this an equal sign. We can approximate it. If we do this for the one that we just did, 6.626 4 pi times, what did we have for M and V? 9.11. 7 times 10 to the 7th meter per second. Notice that this is the same thing as your de Broglie wavelength divided by 4 pi, just for your information. So, because those first three numbers were our wavelength, divided by 4 pi. So if we do this, what was our answer? We had 1.04 times 10 to the negative 11 over 4 pi. And this is kind of going to be a bad example, I realize, but that's okay. So take this number divided by 4 pi. We get, and this is not a problem at all, 8.27 times 10 to the negative 13 meters. So we have an uncertainty here of somewhere around the 10 to the negative 13th meter. Bad example because this thing happens to be moving really quickly. Let's slow it down to more realistic ones so we can see the point of this. So I'm going to use a slower velocity. Let's say we're going 50,000 meters per second. Instead. So we're going to slow this down. If we do this, Planck's constant, uh, 4 pi, mass, and this 50,000. This I'm just doing to show a point, and I happen to choose a bad speed. So that was too high. So if we do this, I'm going to go ahead and erase 50,000. There we go. Aha! Doing this with this new one, 1.16 times 10 to the negative 9 meters. So this is the uncertainty. This is how uncertain we are. That means our error in measuring the distance of where the electron is off potentially by 1 times 10 to the negative 9th meters. If an atom is 1 angstrom in radius, which some are, this tells us, so here's our atom, and it's 10 to the negative 9 meters is this distance. So if we want to say our electron is right there, our uncertainty in this measurement is well over the size of the atom. It's a magnitude, order of magnitude higher. So the electron, as we calculate it, could be anywhere over here. But we know it's got to be part of the atom, right? So the point is, our uncertainty is so large compared to the atom itself that we have limitations on these things. And so it's very hard for us to know exactly where an electron is. We have a lot of uncertainty. We have way more uncertainty. And so we do not really ever know exactly where an electron is. And so as a result, what we use instead, we use probability. And that's where we're going to pick it up on Thursday. So instead of knowing exactly where something is, which would be really lovely, it'd be very informational to know exactly where an electron is. Instead of that, we just will say, okay, well, there's a high probability it's going to be here. There's a low probability it's going to be here. And we're going to see what those probability distributions look like next time. All right? So that's it for today. We'll talk about electron configuration and probability maps and all this sort of fun stuff next time. All right? So have fun. Enjoy your Tuesday. And we'll see you on Thursday. I do have a bit of sad news. I may be a little bit less active in the next couple of days than normal because little Oz, he's going to be going to sleep later today. So I'm going to probably not be in the best place. So just give me a little patience in like responding to your questions and things. Just give me a couple days. I'll probably be back to normal soon enough, but it'll be sad for me. So yeah, just putting that out there. So I beg your patience in the next couple of days. Okay. So here you can say we'll have one last visit. So he'll say goodbye to you all. So you'll see the rest of them more, obviously. So, but we'll say goodbye. Say goodbye, buddy. So, okay, yeah. Sorry for the sad news. Sorry to ruin your days, but yeah. All right. See you on Wednesday.